Then, as we dive into some of these review topics from Gen Chem, I'm assuming that I don't need to spend a lot of time rehearsing atomic structure, that we understand that in any given atom of any element in the periodic table, you've got a central, very massive nucleus consisting of positively charged protons and also uncharged neutrons, and that contains nearly all of the mass of the atom. And then distributed around that, that nucleus in some sense in what we call atomic orbitals that even get combined into molecular orbitals. In some sense, you've got negatively charged electrons that have very, very little mass in comparison. The periodic table will have the atomic number and mass number of any given element, which brings me to another thing that I want to be sure that I say today. I will always give you a periodic table with every exam. I wouldn't dream of giving a chemistry exam at any level, freshman, sophomore, junior, senior, without giving out a periodic table. That would be flat out immoral. So you don't need to worry about that. I will always give you a periodic table. I would certainly never expect you to memorize the periodic table. Oh, look how naughty this one is. It is only the atomic numbers. I'm not seeing any average mass numbers or atomic masses. I'll have to remember not to use this one then. Be that as it may, it's otherwise a perfectly functional periodic table. This is probably also as good a time as any, how many decimal points? Oh, that's gonna vary. They're all different. I mean, I would just, if you're in the process, the question on chat, I don't know if you guys can see it, was how many decimal points will the masses be? Well, you would just use whatever number of decimal points you're given. But I guess I can't give you this periodic table, right? Because if you need the atomic masses for anything, this one doesn't have it. So be that as it may, try P table it really. Okay, suggestion from chat. Well, I'm not too proud. www.ptable.com. That one's a little bit better. Wouldn't mind if it were a little larger, but that one works. Be that as it may, this is all the information. Either of those would work for what we're going to need this for today. That also brings me to mind, I'm going to go a little bit out of order maybe from my class notes just now, but since we have this periodic table in front of us, oh, I just realized I think I need to do new share. There, now the people in chat should be able to see it. Good, so that also brings to mind that probably it's a good idea to refresh your memory on electron configurations, all that 1s2, 2s2, 2p6 stuff. I think it would be good for you to be able to write the electron configuration certainly for any S block or P block element, your main group elements. Those are the ones that we're going to need the most. I would never in my wildest dreams ask anyone to write the electron configuration of an F block element, because I don't know what they are. They're full of exceptions. The D block elements I think you can do. There are exceptions in the D block, but they're consistent. They go all the way down the column, right? Remember, for instance, that the chromium column, you would expect this column to be D4, but remember, it steals an electron from the S subshell in order to make the D subshell half filled, because that lowers the energy. So chromium, for instance, would have all the electrons in argon, and then it would be 4s1, 3d5. And molybdenum would do the same thing, except the numbers would go up by 1. And likewise, in the copper column, you have exceptions like that as well. You would expect these to be D9, but they're actually D10, because there's a significant energy lowering when it steals an S electron and you get your D subshell fully filled. So silver, for instance, would have all of the krypton electrons, and then 5s1, 4d10. So there are exceptions in the D block also, but at least they're regular, at least they're consistent. The exceptions in the F block aren't even consistent. So I think that would be good for you to be able to do any of those electron configurations, or simple ions, right? Like Br minus, or I don't know, Na plus, you know, Ca2 plus. Those I think are pretty basic. So I'm not really going to spend any time in class reviewing those. Could there be electron configurations on the first exam? Absolutely. Absolutely there can. It's in chapter 1. It's part of the class material. It's something assumed from Gen Chem. Now, if the exam's out of 150 points, am I going to make 60 points out of that 150 electron configurations? No, not so much. I don't think so. You know, it wouldn't be that much, but it's fair game. You know, I think I would be a little more reasonable about it than that. So they've named some of these elements: fluorovium, livermonium, tennessine. Great. Sounds like we're making it up as we go. Oh, wait a minute. Yeah. So we're not using that screen any longer. Let's share the class notes so that the people in chat can see it. Good. So I think that's all we'll need today, other than the whiteboard, which, thank goodness, seems to work pretty well. Good. So with that, we've reviewed about orbitals, atomic orbitals. You'll want to review that terminology. I already mentioned electron configurations. Basically, for the rest of the time today, I want to talk about chemical bonds. I think you'll agree those are pretty important. Just reminding you about how they arise and what they're like. And I'm actually going to save drawing Lewis structures mostly for our last topic today. And that's going to bleed over into Monday as well. That sounds a little bit violent, but I didn't mean it to be that way. But I think there's no point actually drawing Lewis structures until we go over the theory of chemical bonding, just a little bit. We're not going to use too much molecular orbital theory in this class. There will be some places where it's unavoidable. One place I'm thinking of is going to be for sure next term when we talk about aromatic compounds like benzene and compounds related to benzene. It's unavoidable. We have to go there with molecular orbital theory. The other place that we really need to think about molecular orbital theory a little bit is when we get to everyone's favorite topic, resonance. And again, I anticipate we'll mainly talk about that on Monday. Otherwise, the valence bond theory works pretty well. Valence bond theory is a very simple-minded way of thinking about chemical bonds. And in truth, 90 to 95% of the time, at a conservative guess, is going to be good enough for us in terms of how we think about chemical bonds. And again, valence bond theory is very simple. It just says that two atoms, if they're going to form a bond, find some distance from each other that's like the ideal distance, where the internuclear repulsion isn't too strong, where the electron-electron repulsion isn't too strong, and there's the exact right amount of balance in between those two types of repulsion and the attraction from the electrons to the two nuclei. There's some distance that's just right. Now, I do want to remind you, as we say that, please don't forget that molecules are not, where did chat go? There it is. I do want to remind you that molecules are not these stiff, rigid objects like pieces of furniture. They're in constant motion. And yes, there is a bond distance, but bonds are vibrating. There's other modes of what we call transitions. Later on, when we get into spectroscopy, we'll talk more about that. It depends what type of electromagnetic radiation is used. But there's all kinds of different motions that molecules are going through at all times. There's vibrations of the whole molecule, as it were. They're tumbling in space. They're traveling through space. All these things are happening all at once. That being said, for any given bond in any given molecule, there's some average ideal distance. And by that, that's what we mean when we talk about the bond length. Let me also just put you at ease about this. Of course, I don't expect you to memorize any particular bond lengths. I would never do that to you. What is the length of the carbon-oxygen bond in methanol? No, of course not. One thing you'll learn about me is I'm in general not a big fan of people just memorizing tables of numbers. I don't think that's a good use of your time. It would be really great if you were aware that single bonds are longer than double bonds are longer than triple bonds, other things being equal. And single bonds are weaker than double bonds are weaker than triple bonds, other things being equal. That'd be really great. That's helpful to know. But memorizing exact numbers, no, I would never ask you to do that. Same thing with bond dissociation energies. You can find a table of these in the book. OWL may give you some problems, I think, where you're manipulating those numbers a little bit, and it will give you whatever numbers you need. And I would do the same if I ever asked a problem that involved that. I would never expect you to memorize particular bond dissociation energies. Let's see now. I just want to. Okay, so here's our bonding. I should maybe put this in a somewhat different order. Good. So this is another interesting fact that I think is worth being aware of. Forming a bond is always exothermic, always releases energy in the form of heat, and breaking the bond is always endothermic, always, no exceptions. Now, some bonds, when they form, don't release a lot of energy when they form. They're kind of weak bonds, and you can find out which bonds are weak and which are strong relative to one another when you take a look at that table of bond dissociation energies. So some bonds, when you form them, they don't release a great deal of energy. Others, when you form them, release a tremendous amount of energy in comparison. And the opposite's also true. Some bonds are relatively easy to break, do not require a lot of energy input in the form of heat, because they're weak. Those bonds are not very stable. In comparison, other bonds, when you break them, requires a tremendous amount of energy to break them. Like the nitrogen-nitrogen triple bond in the nitrogen molecule, N2. It's a very, very strong bond. Takes a lot of energy to break that. When you're going in the other direction, when you form a bond like that, it releases a tremendous amount of energy. Other bonds are kind of weak. Most bonds between nonmetals are pretty weak. The oxygen-oxygen single bond is quite weak. Double bond's pretty strong, but the single bond's pretty weak. The single bonds in halogens, Br2, Cl2, these are pretty weak. The main and interesting exception to the idea of bonds between nonmetals being weak, what about carbon-hydrogen bonds and carbon-carbon bonds? Those are quite strong. And it's for that reason that we have the molecules pertaining to life as we understand it. Is because carbon-carbon and carbon-hydrogen bonds are so strong that you can build large molecules consisting largely of these bonds, right? And that's why we're even here to talk about it. So that's one interesting feature. But other than that, by and large, bonds between nonmetals are pretty weak. Just to give another example, compared to carbon-carbon and carbon-hydrogen bonds, silicon-silicon and silicon-hydrogen bonds are pretty unstable. There are compounds like that, but they can't be very large or they'll just fall apart. Those bonds are very weak. Silane, SiH4, is sort of the silicon analog of methane. And silane is stupidly unstable. It's a thing. You can get your hands on it. But if it's exposed to air, it just immediately bursts into flame and gets burned up. Methane, CH4, certainly is flammable, but as long as you don't light a match, it's quite stable. So that's why any 60s and 70s science fiction B movies to the contrary, I'm no cosmologist, but my understanding is that for there to be any conceivable kind of life if life does exist on other planets, as we understand life to be, it's pretty much got to be carbon-based, because that's the only way we can make molecules that contain a lot of information and are large molecules. So, like I said, we'll get back to Lewis structures in a bit. I want to so we have until 12:50. I just want to make sure that I stay on track. I do want to talk about hybridization and also the idea of the VSEPR model, since you might have been fed some good solid lies about that, or at least maybe not emphasized quite the way I would like to do so in your Gen Chem class. I shouldn't accuse your professor of lying, but I'll just say this. The VSEPR model or the VESPR model is something they always make out to be this hugely, tremendously complicated thing. And it so isn't. It's dirt simple. And I hope to convince you of that before the end of the day. Any questions either from chat or, I have to remember to turn around the entire way. Or so far so good? Hopefully ringing a bell from Gen Chem. Well, let's kind of take care of hybridization and molecular shape in the VSEPR model kind of all in one fell swoop. Let me also then switch to our whiteboard, since I think that will be more convenient, as then I can draw some structures for you guys. So molecular shape and hybridization are very closely related. I really do think, I'm confident that I'm safe in saying this, I really think that the only hybridizations you guys are going to need to worry about, either this term or next term, is sp3, sp2, and sp. I think those are it. You might have learned some other, I see your question, you might have learned some other sort of bizarre hybridizations, especially in Gen Chem 2, if you talked about transition metal complexes. You might have done like dsp2, d2sp3. I don't think we're going to need those. I don't think we're going to be doing any hybridizations that involve d orbitals. Question on chat, as you might have noticed, will I still be posting lectures to YouTube? Absolutely. So I will always take either your lecture or the one from the previous class. Frankly, this class is going about 5 times better than the previous class. So I think last time I used their class, this time I'll probably use this one. So, oh, great, now they're all gonna see. Maybe I'll cut that out. I do want to do some, at least light editing of the video also. For the last one, I think I just trimmed the ends so that we were staying pretty much on topic. But it's like, just like those people who are having classes completely online, so those professors are putting the lectures on YouTube beforehand. I'd like to do the same thing, but after the fact. That way you can always go back and listen again. So yeah, I got some practice doing that last term, and it's not that difficult. So I do plan to keep doing that. Just be sure that you're looking at 227 lectures and not 222 lectures, since I'm teaching both classes. Good. So on the topic of hybridization, one thing that I always found kind of frustrating, and I imagine must be frustrating for you guys too, to be completely honest, is how hybridization is defined in terms of molecular shape. And the thing that's frustrating about it is they're defined kind of circularly. You know, if someone asks, well, what is sp3 hybridization? They'll say, well, it's the hybridization that a molecule takes when the central atom is tetrahedral in general shape. And you say, well, how does it form a tetrahedron? Well, by being sp3 hybridized. So you see, it's very circular. And unfortunately, we're kind of stuck with that. The only way to break that kind of circular definition is by getting into really heavy-duty molecular orbital theory. Although we can get some idea as to how to answer that question from the VSEPR model, which luckily, as I've said, is very, very simple-minded. And we'll get to that today as well, maybe even next. So, but basically what hybridization means for us is that there's really only 3 possible shapes that you can have around any given atom. And they're tetrahedral, trigonal planar, or planar triangular, or basically the shape of an equilateral triangle, or linear. Those are really the only 3 shapes we have. Now, an atom can be tetrahedral, like the central carbon atom in methane, or any other sp3 hybridized carbon. Here I have, like, I want to make sure where'd my picture go? Oh, that's right, you can't see my picture because I'm on the whiteboard. So, wait a minute though, where's, not that I really want to look at myself, don't misunderstand me, but where's my camera? Yeah, I have to select a camera. Bottom right corner. Oh, it's this thing? Oh, well, oh, there we are, yes. That can probably be done better, but at least now it's on the screen. Okay, so I was right. I was talking about like the central sp3 hybridized carbon atom in a molecule like methane, or can even be up to 4 different groups attached to the carbon. That central carbon atom will be tetrahedral, but it doesn't have to be 4 bonds, right? This is where the VSEPR model comes in. It's just 4 places where there are electrons, where there's electron density. So the central oxygen atom in water is also basically built on a tetrahedron, right? The 2 bonds to hydrogen are to 2 corners of the tetrahedron, and at the other 2 corners of the tetrahedron, you would then have the 2 non-bonding lone pairs on the oxygen. So that's what we mean when we talk about sp3 hybridization. It means that that atom is essentially built upon a tetrahedral template. And in order to get that shape, you have to have sp3 hybridization. So this is what you'd find in the central carbon atom of methane, or the 2 central carbon atoms of ethane, which is C2H6. It's just replace one of the hydrogens on methane with another CH3, and you have ethane. And we'll learn about naming hydrocarbons also as time goes on, probably in chapter 2. So in terms of drawing that, let me just switch to the whiteboard for now. One thing I want to get down as clear as I can from the beginning is there's always many, many possible correct ways to draw any given structure, all of which would be accepted. There's all kinds of room for individual taste and individual variation. Again, as long as we count to 4, right? Carbon should have 4 bonds. But, you know, one could draw methane, for example, just like that. Perfectly acceptable. But of course, that structure doesn't reflect the shape of the molecule. And the way you know what to do is by what an OWL question is asking you to do, for instance. Sometimes it will say you need to account for correct molecular geometry. Other times it'll say don't worry about molecular geometry. A flat structure is just fine. But certainly that structure contains all of the information we need in terms of how the atoms are connected and where all the electrons are going. If we wanted to show the correct molecular geometry, that we have a tetrahedral molecule, well then, we would need to use wedge and dot bonds. And again, with sp3 hybridized atoms, we have to use wedge and dot bonds if our goal is to show the correct molecular geometry. We have no choice. It can't be avoided. So again, the flat structure isn't wrong. Oh, now I have to do something. Yeah, those of you asking in chat, I was using this model here of a tetrahedral atom a little while ago. There was a time when I had forgotten to turn on the camera, but that's what I was doing. I'll leave the camera on for the time being. Now, those of you in chat, can you see the structures I just drew on the whiteboard? Or, oh, good, okay. Well, then we'll leave. In that case, I won't touch anything. Okay, so that's sp3 hybridization. What about sp2? Well, it's important that you guys understand that just as with sp3 hybridization, that's what we're always going to find when an atom is saturated, you know, when it has all the bonds that it can possibly have. Carbon can't have more than 4 single bonds. So whenever anything's saturated like that with single bonds, I think you're going to find that it's sp3 hybridized. So sp2 hybridized, so here the carbon is sp3 hybridized. sp2 hybridization comes in in molecules like ethylene, C2H4. So we need the sp2 hybridization in order to accommodate that double bond. And they don't have to be two carbon atoms. The same would be true of a molecule like formaldehyde, CH2O. Here I'm also putting in the lone pairs on oxygen. That carbon also would be sp2 hybridized. And in fact, so would the oxygen be. So we need that sp2 hybridization to accommodate a double bond, no matter what atoms the double bond, no matter what kind of atoms the double bond is between. There's no exceptions. If you've got an atom with exactly one double bond, must be sp2 hybridized. I can't think of a counterexample. And I have a model here somewhere. Oh, there's my ethylene. So again, I want to make sure I'm on the screen. It's probably still going to be somewhat small, but this would be a pretty good model of C2H4, of ethylene. And we'll learn later about naming compounds. But I think what you can see is that the molecule as a whole, in terms of where the atoms are, is flat, it's planar. And that's why we say that sp2 hybridization involves trigonal planar geometry, or triangular planar, or planar triangular, depending on the textbook you had. And so remember also that a double bond is always going to consist of one sigma bond and one pi bond. Always, 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 no exceptions. A double bond is always one sigma plus one pi. And the sigma bond is going to have its electron density along the internuclear axis. So this model is actually pretty good. This was left for me by my predecessor. Meanwhile, the pi bond is going to have two regions of electron density above and below the internuclear axis. So these are both of them the pi bond, both at the same time. And so that electron density lies above and below the internuclear axis. And the sigma bond is along the internuclear axis. So that would be a good model of a molecule like ethylene, which is this one over here. The model would work pretty well for formaldehyde also. The only difference is in replacing one of these carbons with an oxygen, instead of having two bonds coming off of that oxygen, right? Because oxygen just wants to have two bonds. Instead of bonding electron pairs there, we would just find those two non-bonding lone pairs on oxygen. But the shape is the same. Both atoms are sp2 hybridized. Both atoms are trigonal planar. Now, what about sp hybridization? That comes about in two different situations. Probably the by far more common situation is whenever you have a triple bond. And this model would be good for a molecule of what's known as acetylene, which is C2H2. Not a very good bond. Let me do that a little better. There we go. So the two central carbon atoms in this molecule are both sp hybridized. They need to be in order to accommodate the triple bond. And all triple bonds, regardless of what the atoms are that they're between, all triple bonds will always consist of one sigma bond. You can see again that electron density sitting along the internuclear axis. So that's one sigma bond plus two pi bonds that are perpendicular to each other. One of them will have the electron density sitting above and below the internuclear axis here, and the other one is perpendicular to that. The electron density is in front of and behind the internuclear axis. So that's a typical triple bond. And by the way, while we're at it, quadruple bonds are not a thing. At least not in anything I've ever heard of. Certainly not in organic molecules. I know someone's gonna come out, one of my inorganic chemist friends will go, oh, there's a thing with vanadium, which, okay, but with carbon, you got single, double, and triple bonds, and that's it. Same thing with the other main group elements. This would be a very similar situation for a molecule like HCN, hydrogen cyanide. There's also a triple bond between the carbon and nitrogen there, and the model will still work. That nitrogen is also sp hybridized, as is the carbon atom, sp, sp. So the only difference is instead of a bond coming off of the nitrogen, that's where that non-bonding lone pair will be in order to complete the octet on nitrogen. but both of those involve sp hybridization. That's by far the more common type of, or that's the more common situation where we would need sp hybridization. The other one that you run into, which is rare, but it occurs, is where you have two double bonds that are what we call cumulated. And we'll learn about terms like that, I think, in chapter 10. What that means is the two double bonds are coming off of the same atom. And one molecule that I think you're, can I do Control Z? Ooh, good. That I think you're all familiar with that shows this type of bonding is none other than CO2, carbon dioxide. And there you'll find that the central carbon atom has to be sp hybridized. It has no choice. Otherwise, it can't accommodate those two cumulated double bonds. The oxygens, I would expect, would be sp2 hybridized because they include a double bond. But the carbon has to be sp hybridized. Another molecule that does that you might run into in your travels, kind of a bizarre one, C3H4. And here I'm going to try to draw it using the correct molecular geometry. This molecule happens to be called allene, A-L-L-E-N-E. Not that I really care if you know that. But in case you're curious, it does have a name. And here, the two carbon atoms would again be sp2 hybridized, just like those two oxygens would be. And the carbon has to be sp hybridized. And again, it has to be. There's no other way that it can accommodate those two double bonds. And again, what you find is the two double bonds are perpendicular to one another, just like in a triple bond. So the two pi bonds in those two double bonds are perpendicular to one another. That's why two of the hydrogens are in the plane and the others are pointing out at you and pointing into the plane of the screen there. So it's an intriguing situation. Propydiene, good job. You can also call it that. Propydiene would be, or 1,2-propydiene would be the IUPAC, you know, the technical name. Allene is what we call the trivial name. People would generally call it that. Again, I don't care if you know these names, at least not now, but I just am mentioning what it's called in case you're curious. Good, so those are the types of hybridization that I think we're going to be dealing with. I don't think you'll need any others than sp3, sp2, and sp. Make sense? So weird, teaching in the round. All right, let's see what else we have then. Let me switch to the class notes again, at least for now. So we've covered those types of hybridizations. That leaves us 6 minutes to get started on drawing structures. And by the way, if I were to tell you what I suggested in terms of your practicing this weekend, get in there and draw structures. Just doodle, copy them from the book if you need to, so that you know you're doing it right. Maybe then redraw it, turn it at an angle and redraw it. It won't be wasted time, I promise you. I've given you in the class notes one method for drawing Lewis structures. It's not the only way. You might find it useful at the beginning as you refresh your memory again. But this is one way of doing it. I've also reminded you here of the formula for formal charge. I would say probably 98% of the time, when you look at any given atom and any given molecule, the formal charge should be 0. Sometimes we'll run into +1 and -1. I don't think we'll ever run into anything beyond +1 or -1. It should be one of those 3 numbers. Good, and I've given you other tips here. When atoms have 0 formal charge, this is the number of bonds and lone pairs that you will find. Should you memorize that? I mean, I guess so, except I think that after you draw enough structures, you'll automatically wind up memorizing it. So same thing with these situations with +1 and -1 formal charge. So I'm just leaving these in your class notes just so that you have them as a reference. But just to give an example, let's end by drawing a molecule or two. Let me first, I think I figured out how to do this, so eraser. Whee! It's a little bit tedious, but it eventually works. Oh, fascinating. Okay, I'll try to remember to use that next time. So let's see. Well, I know, since I see we have 3 minutes, that's probably, that was bad. That should be enough to do, at the very least, CH2Cl2, whoops. That's kind of what I ended with my other class. So let's draw the structure of this one. You'll recall that in general, I mean, there are exceptions occasionally, but in general, the central atom is going to be the least electronegative element. And I don't care if you memorize Pauling electronegativities, you should be aware of the trends, you know, that electronegativity increases, let's see, from left to right, and it also increases up the periodic table, right? So fluorine is the most electronegative element that we're going to run into in terms of bonding. But even without being sure of any of that, of the electronegativities, I think we can tell already just by looking at the formula, the carbon had better be the central atom, because hydrogen and halogens can only form one bond and have a formal charge of, well, hydrogen for sure can form only one bond in all cases. Halogens can have multiple bonds, but then they don't have a formal charge of 0, and we want our chlorines to have a formal charge of 0. So after that, we'll distribute our peripheral atoms around that central atom in some pleasing geometric shape, assuming that it's not asking us to draw it also in the correct molecular geometry. That would require, in this case, wedges and dots. And we also, of course, have to count valence electrons. So this is where your periodic table will come in handy. Carbon will have 4 valence electrons. Each of the 2 hydrogens will have 1 valence electron. And halogens have 7 valence electrons, all of them, fluorine, chlorine, bromine, iodine. So 2 times 7 is 14. And unless I've completely lost it, that means we have 20 electrons to account for. It means we have to use all 20, and we can't have any more than 20, and we do have to use all 20 that we have. So the first 8 electrons are going to get dropped in as covalent bonds between the central atom and the peripheral atoms. And you can also refresh your memory on when to draw multiple bonds. We did formaldehyde earlier, so you can check that one out, for instance. I like to make sure that I'm accounting for all my electrons, so I've used 8 of the 20. We've got 12 electrons left, and we have to use them. The rules then state that you'll use any leftover electrons in order to complete the octet, first on the peripheral atoms, and then if there are any left over on the central atom. I think you'll find we'll use all 12 here. 2, 4, 6, 8, 10, 12. And that's it, we've run out of electrons. All of the atoms obey the octet rule. There's no need for any multiple bonds here. And so we're done. That's only one correct way of drawing it. You could have put the chlorines and hydrogens anywhere in the flat structure. You will get, it's an equivalent way of showing the same thing. And with that, believe it or not, I'm out of time. But we'll pick up here on Monday. We'll get more into drawing structures, and we'll get into some of these tricky wickets like resonance and so forth. So other than that, have a great weekend, and we'll see you all on Monday.